In today's lecture, we'll see what are the military applications of nanoscience and technology. Right. So, in the previous lectures, we have seen the fabrication of nanotechnology, and we have seen the fabrication of nanomaterials by using different process like PVD, CVD, right? And after that, we have seen certain characterization of materials. After this characterization, we have seen certain differences. We have seen certain differences between certain differences between the characterization techniques. Right, like what is the difference between AFM and MFM? What is the difference between scanning electron microscopy, transmission electron microscopy, right? And what is XRD and all. So we have seen certain different techniques like neutron diffraction and all, right? And after that, we have seen what is how the thin film nanostructures are fabricated, and we have seen certain applications, right? So in that applications, in today's lecture, in that application, we see what are the military applications of this particular nanoscience and technology, right? So future military missions require its stakeholders to do more with less. So nanotechnology offers military stakeholders to get more performance, right? So one of the important application where nanoscience and technology can be imparted, is in where the importance nanotechnology and nanoscience can be imparted is in military applications. Because military applications, defense applications, right? So defense applications plays an important role. So defense applications, the nanotechnology plays an important role in defense applications. Right? So that's what the future military missions require its stakeholders to do, right? So to do more with less, that means to do more with less, nanotechnology offers military stakeholders, right? To get more performance, functionality and lifespan, right? With less weight, size, maintenance, power and cost. So keeping these particular features, the stakeholders keeping these particular features in mind, and they have to develop such a material that it gives more performance. So the functionality of the material should be more. At the same time, the lifespan of the material also should be more. Right. So future military applications require its stakeholders. Right. So to do more with less. So to get more, and we need these particular features with less quantization. So with less maintenance, right? So it should be the weight of the material, the weight should be less, and the size dependent, and the maintenance of that particular device also need maintenance. See how far we can maintain that, right? So what are the advantages of maintaining, and what are the disadvantages of maintaining? So that's what. At the same time, what is the power required for that material to function? And what is the cost? What is the commercial cost of that particular device, or a particular device that can be used to get more performance, functionality, and lifespan? So nanotechnology offers military stakeholders. So we need the output more with less durability, like the parameters like weight, size, maintenance, power, and cost. Right. So in the presentation overview, what is nanotechnology? How nanotechnology is impacting military technologies, uses of nanotechnology in military applications, implications for DRDC, implications for Defense Research Development Corporation and Canada, right? Implications for DRDC and Canada, right? So Canada plays an important role for the briefing of this particular technology. So that is what the presentation overview requires, right? So what is nanotechnology? We all know. So the nanospace is micro, so 1 millionth of meter, nano 1 billionth of meter, pico 1 trillionth of meter, right? Micrometer sized grains in materials, microelectronics, electromechanical systems, MEMS devices. So visible optical wavelengths. So you can see the device. So this is what the device what we can see. So this is what the device. That is a MEMS device, right? So this is a MEMS device, and we have the 1 billionth of meter, that is from top down to nano, right? 1 billionth of the meter top down to nano, and from atoms, molecules, so it becomes the bottom up. So top to down in the sense, so 1 millionth of meter, that is micro-sized material, micrometer-sized grains in materials, microelectronics, microelectromechanical system, MEMS, visible optical wavelengths, So to top-down approach, it comes to the nano stage, and that is what 1 billionth of meter, and pico is 1 trillionth of meter, and pico is 1 trillionth of meter, right? So this is what we can see the overall mission, overall space mission, overall the nano space mission, right? So micro means 1 millionth of meter, and nano means 1 billionth of meter, and pico is 1 trillionth of meter. Right, so atoms, molecules, small and molecules. Atoms, small molecules, they go to the bottom up, give nanostructure, and from there it goes to the top bottom, and material sized grains in materials, microelectronics, electromechanical systems, MEMS, visible optical wavelengths. So these are the certain features where we can see the nanospace mission. So nanotechnology enables miniaturization beyond micro. Nanotechnology enables miniaturization beyond micro. The International Technology Roadmap for Semiconductors. So, International Technology Roadmap for Semiconductors. This is what the acceleration continues. So, this is what the feature size nanometers, right? To 350 nanometers, it is coming to 250, 180, and 25. And then the year of production 95 to 97, 99, 2001, 2004, 7, 10, and 10 axis, right? So, this is what the opportunity, and this is what the price list, right? So this is what the price performance. This is what the price performance, and this is what the the opportunity that required for the opportunity required for the production. Opportunity required for the production, right? So there is an international technology roadmap for semiconductors. So that is what the acceleration continues. Feature size nanometers, right? So miniaturization delivers better products at lower price. Miniaturization delivers better products at lower price. So that is what lab in a building result. Lab in a building, lab in a box results in hours. Lab on a chip that's used in minutes, right? So earlier labs in a building, that is what it. Lab in a building results in a number of days. How much it is? How much time duration is dependent. And lab in a box results in hours, right? Results in hours. So that is what lab in a building results in days. So lab in a box results in hours. Okay. And lab on a chip, that is what results in minutes. Lab on a chip, that is what results in minutes. So results in minutes. Lab in a box, lab in a building results in days. So miniaturization delivers better products at lower price, right? Implication 2. So properties of materials change dramatically at the nanoscale. Properties of materials change dramatically at the nanoscale, right? So different laws of physics apply. Behavior of surfaces and grain boundaries. Dominate. So different impact of light or mechanical electromagnetic effects on particles. So first case of implication. This was the first case of implication. How the nanotechnology enables miniaturization beyond the microtechnology, right? And the second case, what is the physics behind that? So properties of materials change dramatically at the nanoscale, right? So different laws of physics apply. So properties of material change dramatically due to the different laws of physics. So behavior of surfaces and grain boundaries. Dominate. And different impact of light or mechanical or electromagnetic effects on particle. Nanometer sized particles are smaller than ultraviolet rays and can completely block ultra very and UVB lights, right? So the ultraviolet rays and can completely block UV ultraviolet rays and UVB ultraviolet in blue when dispersed in sunscreen. So this is what we can see here. So scatterers visible light produce skin whitening. So this is UV blocked. This is what UV blocked one, and this is UV blocked. This, and this is visible light transparency. Minimal light scattering, no skin whitening. So source is APT Z-clear. APT zinc clear. So from there, this particular material has been taken. So from Canadian Nano Business Alliance, right? Canadian Nano Business Alliance, which was imparted at a symposium in 2005. Okay, so that is what DRDC, Defense Research Development Corporation, and SNT Symposium was taken there. So the properties of materials change. The properties of the materials change at very low dimension, at a low scale. That is what people tell. There is plenty of room at the bottom. So that means for that, the properties to get changed, we need to apply different laws of physics, and behavior of surfaces, and what is the importance of grain boundaries. So how the grain boundaries dominate these features, and different impact of light to mechanical or electromagnetic effects on particles. So nano-sized particles are smaller than ultraviolet rays. Sized particles are smaller than ultraviolet rays and completely block ultraviolet rays and ultraviolet blue when dispersed in sunscreen. Right. So this is what we can see, certain UV blocker and UV visible lights. Right. UV blocker and useful light. So nanomaterials is expected to greatly reduce the volume of materials required by industry. Nanomaterials is expected to greatly reduce the volume of materials required by industry. So this is what the capital intensity and knowledge intensity. So this was not the variation that we observed when we see the variation between the revenue developed and physical volume of goods sold. So these are what the chemicals. So this is what the capital intensity, where we need to buy some chemicals. Okay, and this is not this is what the knowledge intensity. So capital intensity and knowledge intensity. So chemicals rise up, and yesterday the chemicals, today we have the normality between the chemicals, and tomorrow we know how they are fabricated, how they are being done. So that is what the revenue that is developed, how the revenue and physical volume of goods sold. So nanomaterials is expected to greatly reduce the volume of materials required by industry. Right. So this is what one of the most significant feature. Right. So that is what the implication 2, and this is the implication 3. So in implication 1, we have seen how it is showing in the market from the year 1995, and implication 2 shows what are the physics behind the materials. Right. And implication 3, so nanotechnology allows researchers to work on the scale of nature. Nanotechnology allows researchers to work on the scale of nature. So nanotechnology, nanoparticles whose size is 1 to 100 nanometers, and fullerene, which are nothing but the two-dimensional two-dimensional nanomaterial, nanotubes, we can tell. Fullerene, which is nothing but the carbon 60. So whose dimension is approximately approximated to 1 nanometer. And nanotube, a single wall nanotube is 1 nanometer into 50,000 nanometer. And quantum dots, which is cadmium beryllium, which is 8 nanometer, and dendrimeter, which is 10 nanometer, and nanotube multi-wall, that is 20 nanometer into 50,000 nanometer. So from this nanotechnology, the nature of the particles, the atoms is 0.1 nanometer, and the width of the DNA is approximated to 2 nanometer, and protein is 5 to 50 nanometer, virus is 75 to 100 nanometer, materials internalized by cells is less than 100 nanometer, bacteria is 1000 to 10,000 nanometer, white blood cells are 10,000 nanometers. These are what the implication in 3. Nanotechnology allows researchers to work on the scale of nature. Okay, nanometers to 1 to 100 nanometers. Fluorines are carbon nanotubes, which is 1 nanometer nanotube, single wall 1 nanometer to 50,000 nanometers. Quantum dot, cadmium selenium 8 nanometer. Dendrimer, which is 10 nanometers. Nanotube, multi-wall nanotube is 20 nanometer into 50,000 nanometer. And the nature, if you go for the nature, atom is around 0.1 nanometer, DNA width is 2 nanometer, and the protein is 5 to 50 nanometer, virus is 75 to 100 nanometer, and materials internalized by cells is less than 1000 nanometer. So white blood cells is around 10,000 nanometer. So this is what the implication 3 is. So nanotechnology and nature will bring up the convergence of multiple roadmaps. So we have how they are made, known how, and what are the products and what are the applications. So we have the biotechnology and electronics. So biotechnology includes bioinformatics, systems biology, and electronics includes the design and simulations, and micro or nano lithography. The lithography is a patterning part, and the other one is a lab on a chip design. Lab on a chip where the nanosensors, the electronics plays important role in nanosensors, and whereas in biotechnology we call the nanofluidics and nanoarrays. So these are the products that are obtained, and the applications, various applications where they are used for a clean water research, and there's a biothreats, and for the electronics which can be imparted for agriculture and food, and at the most they are used for drug discovery, and finally we have clinical assessment. So nanotechnology in nature, that's what will bring the convergence of multiple roadmaps. So this is biotechnology, and we bring the difference between biotechnology and electronics. In electronics, we have design and simulation, micro and nano lithography, and lab on chip, nanosensors, nanofluidics, and we have agriculture and food. So these nanofluidics, nanosensors are nothing but the biothreads. So these biothreads applies a clean water and clinical assessment and drug delivery. So that's what nanoscience, this technology and nature will bring the convergence of multiple roadmaps. Right? So this is one the other implication. Implication 4, nanotechnology opens up vast new capabilities. Nanotechnology opens up vast new capabilities. Camera that can be swallowed for medical imaging. Systematically organize and manipulate matter from the bottom up and control every atom. Systematically organize and manipulate matter from the bottom up and control every atom. So camera that can be swallowed for medical imaging. That is for source and giving imaging. And systematically organize and manipulate matter from the bottom up and control every action. So these were systematically organize and manipulate matter from the bottom up and control every atom. So this is what required here. Right? And this is what the camera that can be swallowed for medical imaging. This is what the medical imaging camera. Right? So this is what the implication 4 is. So nanotechnology will facilitate the creation of both evolutionary and disruptive innovation. Nanotechnology will facilitate the creation of both evolutionary and disruptive innovation. Right. So this is what the product performance versus time. Right. Sustaining innovation, breakthrough, and pace of technological progress. So this is a disruptive innovation. Sustaining innovation, we have other which is disruptive innovation. So this disruptive innovation comes under the incremental and disruptive, incremental and breakthrough, right? And this is what the phase of technological progress. In nanotechnology, we see the creation of both evolutionary and disruptive innovation. So this is what the disruptive innovation, and this is what the sustaining innovation. So this is phase of technology progress. Right? So evolutionary innovation can be realized as mainstream products. This is market share, and we have the radial tires, bias ply tires, right? So this is what the market share, which is around 0 to 100%, and from 1965 to 1980, the shares have been bias ply. This is what the radial tires has been increased. Radial price have been increased to 100%, whereas the bias ply tires have been decreased from 1960 to 180. Right. So this is what the evolution innovation cannibalizes mainstream products. So disruptive innovation creates new paradigms. Right. So we have the bank branch, that is what computers, telecommunications, and technologies for banks. And before earlier we have the typewriters in branch staff to manually update bank books and branch transactions, tellers, in branch bill payments, security guards. Right. So in bank branch we have the computers and telecommunication technology for banks. So these typewriters have been replaced by PCs, right? And in branch staff to manually update bank books and transactions, automated systems to update bank book and bank transactions. And tellers means in this after the bank branch we have the ATMs, right? In branch bill payment is nothing but telephone bill. So security guards are utilized as security cameras and remote monitoring. So this is what the disruptive innovation creates new parameters. So these are all before people used to use this, and they got disrupted, and people started focusing on these features after that. Right. So this is what the descriptive and disruptive technology innovation that creates new paradigm. So disruptive technologies lead to the disappearance of individual product lines and the demise of entire industries. So this is what the electronic industry is. So top vacuum tube receivers 1955, top transistor CMOS 1955, and top ICs. ICs means integrated circuits. CMOS in 1975. So they are first one in top vacuum tube is RCA, Sylvania, GE, and Raytheon and Westinghouse, and top transistor is Huggies, Transistron, Philco, Sylvania, TI, and top ICs, top IC companies in 1975 were TI, Fairchild, National, then later came the Intel, and now the Motorola. So how nanotechnology impacting military technologies? So this technology is impacting the nanotechnology is impacting military applications is nanotechnology and microsystems are greatly improving the performance of military products and reducing the cost. Nano or micromaterials and devices, low mass and ultra small size, high performance and functionality, resistant to the environment. So lighter craft, we have stronger materials, non-corrosion, radiation shielding, embedded stress detector, less moving parts, example actuators, less fuel, so reduced materialized failure, longer life, lower risk of catastrophe, and less breakage, reduced maintenance, and low downtime. So this is how these particular applications have been incorporated by using the nanotechnology. Nanocomposite materials provide higher strength, lower weight, and a new functionality. Right, nanocomposite using carbon nanotube to enhance the properties of polypropylene. That is what the Korean National Lab, and super tough nanocomposite coating with standard greater point load than the ceramics. AFRL. Right. So this is what the nanocomposite using carbon nanotubes to enhance the properties of polypropylene. That is Korean National Laboratory. Right. So nanophosphorus materials greatly improve the ability to filter and separate nanophosphorus materials. Right. So this is a nanopore. We have DNA sequencing, and we have water desalination filter, right? Miracle water, and we have fuel cell membrane. So fuel cell membrane, which is having so many components like bipolar plate, gas diffusion layer with catalyst membrane, gas diffusion layer with catalyst, bipolar plate. This is what cathode, anode, and cathode, right? So this is what the nanosphere material greatly improve the ability to filter and separate. So nanoscale electrodes provide ultra-sensitive detection and highly focused stimulation. So this is what the brain implant, that is what taken from University of Utah. Right. And we have the electrochemical biosensor, which was taken from the NASA graphs, and this is what the eye chip. So this was taken from University of Tübingen, Germany. Right. So this is what the electrochemical biosensor. So micro and nano systems on a chip provide multiple functionality in a tiny footprint and COTS pricing. Closed post actuator, that is MEMS, moving mirror on a chip, which was taken at Illinois at Chicago, and micro and nano sensor and wireless radio transceivers, and this is what the micro or nano fluidic on a chip, that is what fluidic indicator. So multifunctional materials and smart materials will facilitate disruptive innovation. So such those materials like quantum dots, carbon nanotubes, and smart materials that change its shape when heated or automatically respond to a specific change in the environment, right? Whereas carbon nanotubes are stronger than steel. Harder than diamond, lighter than the aluminium, more conductive than copper, and a good semiconducting material. That is what Ecole Polytechnic. Taken from Ecole Polytechnic. Whereas in quantum dots are nanoscale particle which change their properties in some useful way with addition or removal of electron. So this was taken from Emory University illuminated quantum dots image cancerous tumors. So these are some of the military applications where we can find the importance of nanotechnology. So for that we need to understand what are the main parts of implications. So there are so many implications. First implication is about the market values. So how this market value has been increased in the society by miniaturization. So this is what the miniaturization of the devices. And implication 2 is what is the physics behind it, because this plays an important role in research. What is the physics behind that particular material, and what how the material changes its surfaces and grain boundaries, and how they dominate. So different impact of light or mechanical electromagnetic waves and particles, right? So nano-sized particles are smaller than ultraviolet rays and can completely block ultraviolet rays and ultraviolet blue rays, right? When dispersed in sunscreens. This is what UV and visible screens. So nanomaterial is expected to greatly reduce the volume of materials required by industry, that is what chemicals, and how they are known. How? So this is the next implication. Implication nanotechnology research to work on a scale of nature. So nanoparticles are around 1 to 100 nanometers. Fullerenes carbon nanotubes is 1 nanometer. And quantum dots cadmium sulfide it is 8 nanometer. And deuterium is 10 nanometer. Nanotube is 20 nanometer to 50,000 nanometer. This is what the nature of that particular materials, right? So this is what nanotechnology and nature will bring, the convergence of multiple roadmap. So we have here biotechnology, we have electronics, and we have certain bioinformatics system biologies, whereas in electronics we have micro or nanolithography and design and simulation, and others the lab on chip and nanosensors, right? So this is what the impact for nanotechnology opens up new Western capabilities, and this is what the evolutionary part. And what are the importances of using these particular innovations? Okay, before, earlier, and after, right? So earlier people have typewriters, now they are converted into personal computers. In branch staff to manually update bank book and branch transactions. So for everything is done manually. Whereas here automated systems to update bank books and branch transactions. We have tellers, we have ATMs, in-payment bill branch, telephone bill payment, security guards, security cameras, and remote monitoring are the three features where disruptive innovation creates new paradigms. So this is what the disruptive technologies, right? I have nanotechnology impacting military applications, nano and microscale device, low mass and ultra mass size. Because as we seen in the very first part, that the functionality of that should be more. So we are seeing to get more functionality, phone performance lifespan, with less weight, with less size, maintenance cover and cost. So they keeping that in view, people started working on different materials, right? Nanoparticles around 1 to 9 nanometers, and fullerene, which is carbon 60 is 1 nanometer, and nanotechnology and nanotube is single wall 1 nanometer to 50,000 nanometers. So this is what the implication 3 is, and this is on implication 4, right? So how it is changing in military applications, right? And how this is used in chip designing and all. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.